go with chapter 10 again, talking about circles, and today we are going to talk about tangents. And we need to know that before today we had been talking about things inside the circle, and now we're going to talk about tangents outside the circle. So what is a tangent? A tangent is a line, so it keeps going and going and going, in the plane of a circle that intersects the circle in exactly one point. So if I have a tangent, it's outside the circle, and its LP would be my tangent. Tangent to circle M. Remember, our circle is identified by the center point. So if LP is tangent, it's going to hit circle M in exactly one point, which is point P. And that point actually has a name. It's called the point of tangency, the point of intersection of a circle and the tangent. So because it only hits one point, we know there's only one point that it's tangent to. The tangent is also perpendicular to the A radius, so we can also remember that. A common tangent is a line or segment that is tangent to two circles in the same plane, and that's what we're going to start with first. So we have three different examples here. Draw the common tangents. If no common tangents exist, state no common tangent. So a line or segment that is tangent to two circles in the same plane. So if you look at A, remember tangent can only intersect the circle at one point. So if I intersect these two circles, to be able to intersect the outside circle and the middle, that means I would also have to intersect the other two sides. So if I have a circle inside of another circle, I'm going to have no common tangents. I can only hit it one time. Alright, let's look at the next one. So I have two circles that intersect twice. So if you notice, if I go to the top diagonally, do this the best I can, if my lines would hit both circles at one point right here and right here, that would be a common tangent. So that's one common tangent. I could also go to the bottom side and identify that that would be a common tangent. It's only hitting each circle one time. If you notice, if I try to go through this middle portion right here, I do hit both circles right there, but I would have to keep going. And notice that I hit both of the other circles again, so I'm going to erase that one because that is not a common tangent. So in this example, I'm going to have two common tangents. Alright, in our last example, I have two circles that don't touch. So much like this one over here, I can actually hit both circles on the side one time. And I'm trying to be as exact as possible, but sometimes it's a little difficult. I could also hit it on the other side, so I'm going to go on the top. Alright, so that's two. So something with this middle portion might be helpful. If I go diagonally across, I hit that circle and then I hit the other circle, which allows me to say that that could be a tangent. And if I go one way, I can probably go the other way. Let's see if that's true. It is, okay. So if I have two circles that don't intersect, then I can have four common tangents. Alright, go ahead and stop this video and see if you can find how many common tangents are in your checkpoint with one intersection point. Here is your answer. They intersect one time, so I know I can have 3 common tangents. Alright, our first theorem. In a plane, a line is tangent to a circle if and only if it is perpendicular to the radius drawn to the point of tangency. So my radius has to be perpendicular, or line L is not tangent. If it is perpendicular, then I know that it is tangent at point T, my point of tangency. Alright, LK is a radius of circle K. Determine whether LM is tangent, and we know to be tangent, I know I need to test to see if KL is perpendicular to LM. That's my question. Well, if you notice what I have here in this picture, I actually have a triangle, so I'm going to test to see if triangle KLM is a right triangle, because a right triangle will give me that perpendicular line, that right angle. So I'm going to say, using the Pythagorean theorem, I'm going to say, is 29 squared blank to 20 squared plus 21 squared. And we know this has to be equal to be a right triangle. That's what we learned in the previous chapters. So when I do the math, I get 29 squared is 841, is blank 2. If I combine those two, 841 is also my answer. So that does come out to be equal to, so that satisfies the Pythagorean theorem. So I know I have a right triangle. But I also have that KL is perpendicular to LM, which means LM is tangent to KL, to circle K, sorry. Alright, another example that we can use before we get too far to our checkpoint. In the figure, WE is tangent to point or circle D. So I know it is tangent, so I know because it's tangent, I know I have a perpendicular. I need to find X, or I need to find our radius. Because of Theorem 1010, what we just learned, we know that WE would be perpendicular to DW, we just talked about. So we know that triangle DWE is a right triangle. Alright, with the right triangle, we can use Pythagorean theorem so I know that DE squared equals DW squared plus WE squared. And this is one thing you have to watch out for. DE is this entire length. So it's actually my radius plus 16 more units. So DW is actually going to be X plus 16 squared equals X squared plus 24 squared. I'm going to move this over here. When you go to solve this, you actually have to FOIL X plus 16, because there are two of them, X plus 16. So remember your FOIL method. The first, X squared, plus the outsides, 16x, insides, plus 16x, and then my last, 16 times 16 is plus 256 equals, and then I'm going to finish this portion right here, x squared plus 576. Now, yes, I have x's on both sides, but a lot of times they will cancel. So I'm going to subtract x squared from both sides, and I'm also going to combine like terms. So notice my x squared cancel. I'm left with 32x plus 256 equals 576. Continuing to solve, subtract 256 from both sides. 32x equals 320. So x is going to equal, each radius is going to be 10. So again, I would always look for this to be canceling because that will help us solve something a little less simple than if I have the x squareds involved. Alright, go ahead and try your next checkpoint. Here's your answer. Alright. If two segments from the same exterior point, so same exterior point would be point B, are tangent to the circle. So I know that BA and BC are tangent. Then I know that those segments are congruent. So they come from an exterior point and are tangent to the same circle. They are congruent. So let's try one. AC and BC are tangent. Find the value of x. So because they're both tangent coming from that common point, I know that CA is congruent to CB. And I know anything that is congruent is also equal. So I'm going to say 3x plus 2 equals 4x minus 3. So let's subtract 3x plus 3 on both sides. So I'm going to get 5 equals x, and that would be my answer. Alright, last, go ahead and try your checkpoint. Here's your answer. And last one. Round cookies are marketed in a triangular package for the customer's interest. If triangle QRS is circumscribed about circle T, find the perimeter. Well, we need to find the missing measures since they're all tangent to our circle. I can use our last theorem, so I know that since SM is 10, I also know that SN is 10 centimeters also. What else do I know? I know that QL is, let's find a different color. QL is 2, so I know that QN is 2 centimeters. Well, if this is 2 centimeters, then this would be 2 minus 8, which would give me 6, and because it's, again, tangent to, I would have 6 centimeters over here. So to find the perimeter, I'm going to have 10 plus 10, which is 20, plus 2 plus 2, which is 4, plus 6 plus 6, which is 12. So my perimeter of my triangle QRS is going to equal 36 centimeters. Using that common tangent, to a circle coming from that same point, you can have congruent sides. Alright, well, that is all for section 5, and hope to see you back next time.